Okay, hello grade 12s. So now I promised that we're going to go through the results for the work that we've been looking at before using first principles, and these are the results that we got so far. That when our f of x is either an x squared, then this is the gradient function that we found. Same thing, when our f of x was an x cubed, our gradient function that we found was 3x squared. Similarly, when our f of x was x squared plus 2x, our gradient function was 2x plus 2. Of course, you may not be able to tell the pattern straight off by looking at just this. But then I will say this, if you want, you can go ahead and try it out. You can try and find out that when you generalize, you actually try for x, where your f of x is equal to x, you notice that the gradient that you get is 1. This is kind of evident because if your y is equal to x, remember this reminds you of y equals to mx plus c. And this was your gradient. Remember? And because this is your gradient, in this case, it's a beautiful one. And that's exactly where we're getting this one from. So as you can see already, differentiation or differential calculus works on the gradient for you in very simple ways. Now, what we're really interested in finding now is the pattern that allows us to be able to do it without having to go through the hurdles or the procedure of first principles, and that's exactly what this video is for. Now, if you take a look, we have x, if of x is x, then we get 1. If of x is x squared, then we get 2x. And we proved this true here. So if you would like, you can try and prove this one, and this one to your satisfaction. But then in general, you will notice that if you are given your f of x is, I'm just going to try and generalize here, so please bear with me. Then there is two procedures that you can be able to take, or two steps rather. Two steps that you can take that will allow you to be able to get the gradient function. The first one is bring power down. And then the second step is lower power by 1. So this means that the first step is for you to say this comes the, that gives you n dot a x to the power n. And then the second procedure is when you have that, you then lower the power by 1. So in essence, when we talk about our y being equals to ax to the power n, then the gradient function, instead of using change in y over change in x, we move this, because of the approximation that we made the last time when we say let this approach 0, remember? It changes to dy over dx, and you are going to be talking a lot about dy over dx. Potentially you've heard about it, you've seen it, you've heard people discuss about it. So the reason why it changes from delta y over delta x to dy over dx is because of this approximation that we made initially. And because of that, we're going to come and use it here. So dy, which is the gradient function. So when you do this, you are differentiating. So this process is called differentiating. Okay, I hope it makes sense. Oops, my G won't come up, but that's okay. So I'll give an example. If I have my y being equals to x squared, which is what we had at the top there. So what I'm going to do is, the first procedure is to bring my power down. So I've got my 2 times, and then I've got my x, and then the next procedure is to lower it by 1. And that will give me 2x to the power 1, which is 2x. If you remember, that's exactly what we got here. Similarly, if I have y is equals to x cubed, right? Then my dy, my apologies there, this is supposed to be dy dx. dy dx, which is the gradient function, is I have to bring the power down first, 3x, and then I lower my power by 1, and then I simplify that. That will give us 3x squared. Just to confirm that 3x squared is exactly what we have here. And we proved it using the first principles. And so these are the results. So in other words, when you're given something general, like y is equals to ax to the power n, then your dy dx, which is the gradient function, is going to be equals to n dot a x to the power n minus 1. This is like your first formula. then I'll give you the next one in the next video.